Okay, we'll get back to logarithms here. So I had mentioned in the first video that the domain of a basic logarithm is all positive numbers. We're going to do a couple problems with domain here. So we want the overall input into a logarithm to be a positive. You can't take log of 0, you can't take log of a negative. So in this problem, I would want x plus 1 to be positive. Well, if x plus 1 is greater than 0, that would mean that x would have to be greater than negative 1 for the domain. Part B, I want to find the domain of f. Again, 4 minus x squared, that overall value would have to be a positive. And now in this problem, I've made a graph of y equal 4 minus x squared. That would be a parabola facing downward here. And of course, y positive would mean that you're plotting points above the x-axis. Well, if you're between x equals negative 2 and 2, you're going to be above the x-axis there. And so as long as x is between those two values, the overall number here inside the logarithm is going to be a positive then for us. All right, the next thing that we'd want to know is the natural logarithm. There's a definition there. It says if the base of a logarithmic function is e, then we call it the natural logarithmic function. For notation, we're going to write the ln of x to mean log base e of x. In this next problem here, I am sketching a graph of y equals the ln of x. Okay, now to do that, I want us to first regraph y equal e to the x. Now we had already drawn the graph of y equal e to the x in section 5.3, and I'm redrawing that now. I'm using the same table of values that we had used from section 5.3. Now when you're drawing an exponential, remember x can be anything, so I've got positive, negative, 0, doesn't matter. And I've plugged in these values and got the output and produced this curve here. A feature of an exponential is that there's always a horizontal asymptote on the graph. Okay, well we've already been there and done that before with exponentials. So here's the graph of y equal e to the x. Now remember that an exponential is a one-to-one function. So one-to-one means that the inverse is a function. Okay, and inverse means that you're just switching x and y. Well, if I switch x and y in this equation here, I'll have x equals e to the y. Now, remember the definition of a logarithm says y equals log base a of x means that x equals a to the y. Okay, now here's that definition for when this number a happens to be e. So if I want to graph x equal e to the y, I would have to graph the inverse of y equal e to the x. Okay, well inverse is all about switching x and y. So that's what I'm going to do next. I'm going to switch all the coordinates on these points. Here's negative 2.14, that's going to be at 0.14, negative 2. Negative 1, 0.37, that'll be at 0.37, negative 1. 0, 1 will be at 1, 0. 1, e would be about right here. That's going to be at e1, etc. Okay, and so all these points are going to be switched, and the horizontal asymptote that was on the graph of the exponential is now going to become a vertical asymptote on the graph of the logarithm here. And that's a property of a logarithmic curve, is that there will always be a vertical asymptote on the graph. And here's how I'm getting the graph of y equal ln of x then. Y equal the ln of x is the inverse of y equal e to the x. And remember, that's how we graph any logarithm. We have to first know the corresponding exponential and then graph its inverse. Okay, and also remember that a function and its inverse are always going to be symmetric to the line y equal x. That will always happen, so I've got that diagonal line drawn there again. Okay, now I mentioned in section 5.3 that y equal e to the x is the most common exponential. With that said, y equal the ln of x is going to be the most common logarithm. And in other words, what I mean by that is that there's going to be significantly more math calculations and formulas where you're going to be working with base e more than any other base, more than base 3, more than base 4. Base e is going to come up more than any other base. Okay. The next thing that we want to know is our properties of logarithms. So I've got another handout here. This will be probably on the next page, and they're on the slides. On this handout is laws of exponents. Now these are already in your notes. I had written these on the board in section 5.3. And we've got also laws of logarithms that we'd want to know. Okay, there's 8 laws that are worth knowing. Law 1 says that if you have a single logarithm and you're multiplying the inner terms, you can split that into 2 logarithms that would be added together. Law 2, if you have a single logarithm and you're dividing the inner terms, you can split that into 2 logarithms that would be subtracted. Law 3 is simply saying that powers can come out of logarithms. Okay. Law 4, log base anything, doesn't matter what the base is, log base anything of 1 is always 0. Law 5, if the base and the input number are the same, you always get 1. Okay, so log base a of a would be 1. Here I've got just some calculations to show, why the results are what they are. You can look at that if you want. Laws 6 and 7 kind of go hand in hand because they come from just simply knowing that the 2 functions are inverses of each other. That is, an exponential and a logarithm are inverses of each other. Okay, so if you were to let f of x be equal to log base a of x and g of x be equal to a to the x, remember to check if 2 functions are inverses of each other. You're going to plug each one into the other and check that you get plain old x. Okay, so if I plug a to the x in for x, I'll get x. Well, that's where law 6 is coming from. Okay, and then this other equation, if I plug this logarithm in to this power here, I'm going to have a to the power log base a of x. Well, that's equal to x. Okay, and that is, again, just because these functions are inverses of each other. Law 8 is sometimes called the change of base formula. Sometimes we want to change the base to a new base. We'll see some problems later on where we'll do that. But these are the 8 laws of logarithms that you'd want to know. I've also got some important statements on this sheet here. The first one, we were using this in section 5.3 when we were solving some exponentials. If the bases are the same, you can remove the bases and set the powers to be equal. Statement 2 is the definition of a logarithm. That to me, I think, is the most important part of logarithms, is knowing the definition. Definitely know that. The third statement is also the definition of a logarithm, but for when I've got the base being base e. Of course, the definition would still be the same regardless of whatever the base is. Now, the fourth statement here is a new one at this point. It says that if you have a logarithmic equation and you have the same base on both sides, you can remove the logarithmic notation and set the inner terms to be equal. So m would be equal to n. Now this is an if and only if. Remember what we mean by that. We can read this statement beginning to end or end to beginning, and both would be true. So I could read this also end to beginning. I could say, if I have an equation, suppose m equal n, I can get logarithms involved in the calculation, even though they weren't there originally. I could take log base a of both sides. We'll need to do that sometimes where we're solving an equation for x, and there was nothing with logarithms there, but in order to solve for x, we need to be using logarithms. All right, so a lot of important stuff on this sheet here, and let me get back to my other sheet. So now I've got some examples of where we're using these properties of logarithms. we've already covered this worksheet here, and so in this next example, I want us to, I've got a logarithmic expression, and we're going to write the expression as the sum or difference of logarithms and give the answer without exponents. Okay, so there's some problems like this in the book. Let's take a look at part A. When we simplify, okay, the first thing to notice is that we would be multiplying the inner terms here. From the first law of logarithms, it said that I could split a logarithm into two logarithms that would be added. Okay? And law 3 says that powers can come out of logarithms. Now the square root of x is the same as x to the 1/2. So the square root of x squared plus 1, that'd be the same as x squared plus 1 all to the 1/2 power. And that power of 1/2 can come out of that logarithm. Now this here would be as simplified as we can get it. Okay? We don't have a law that allows us to distribute a logarithmic notation into two terms that are added or subtracted. Okay? So some students want to do that. Don't make that mistake. Part B, when we simplify this logarithm, of course the operation inside is division. So law 2 says that you can split this into two logarithms where you'll be subtracting. Now I don't have a base here. Remember that whenever we don't have the base, it's understood to be base 10. You could write the 10 if you want or not. But I've got base 10. And the last thing that you'd want to do is to bring the powers in front of the logarithm. The cubed root of 2 minus 5x, that'd be the same as 2 minus 5x to the 1/3 power. So that power of 1/3 can come out of the logarithmic notation there. And then, of course, on the other one, the power of 2 can come out in front. Okay, part C. Again, we're simplifying. Now, before I split this into two logarithms, the first thing that I'd want to do is take care of the square root here. I could think of this as, this entire expression is being raised to the 1/2 power. So let's go ahead and bring the power in front. And then we can split this logarithm into two. The operation would be subtraction since I'm dividing the inner terms there. Now I want 1/2 times the whole thing. That would be subtracting these two logarithms. Also, powers can come in front of logarithms, right? So the power of 3 would come in front of that first logarithm. The power of 5 would come in front of the second logarithm there. The last thing is that you could distribute the 1/2 into the two terms there if you want. Okay. The next problem here, I got a logarithmic expression, and we're going to write the expression as a single logarithm. Again, we'll be using our properties of logarithms here. So in this problem, I first want to take care of the 4. Now I mentioned that powers can come out of logarithms. That's law 3. Well, if you have a multiplier, you can still use law 3, and you can pull that number back inside the logarithm so that it's the power of the inner part there. And so that's what I'm going to do to get started here on that second logarithm. Pull that power inside. 3 to the 4th is 81. And now, since I'm adding these logarithms, they have the same base, I can get a single logarithm by multiplying the inner terms together. 7 times 81 is 567. Log base A of 567, you can circle that. That'd be your single logarithm there. Part B, same deal, we'll get a single logarithm. Okay, so 2/3 is a multiplier. I'd want to pull that inside of that first logarithm. 8 to the 2/3 is the same as the cubed root of 8 squared, and the cubed root of 64 would be 4. So the ln of 8 to the 2/3, that would be the ln of 4. And 3 to the 4th is 81, minus 8 is 73. Of course, you don't want to make the mistake where you distribute the ln notation into these two terms. Some students would want to do that. ln 4 minus ln 73, you can get your single logarithm now by dividing the inner terms. You'd be using law 2 in getting that. Part C. Okay, now I've got the same base here on all 4 of these. I'd say, why don't we begin by taking care of the multipliers that are on the first and third terms. You can pull those numbers inside so that they're powers of the inner part. X minus 1 to the 1/2, I'm using radical notation. That's the same as the square root of x minus 1. And I'd say at this point now, why don't we go right to the answer, since we got the same base throughout. The first three terms are being added, so I'd want to multiply the inner parts there. 4 times x cubed times the square root of x minus 1. And then you're subtracting log base 6 of 5. Since you're subtracting, you'd want to divide what you have inside there by 5 to complete the problem then. Okay, and we'll go ahead and stop right there for now.